Welcome back to linear algebra. Let's jump a donkey. Alright. What can you say about the number of solutions of a consistent linear system? A system of linear equations. If it's consistent, it either has one or infinitely many solutions. If a certain sequence of elementary row operations reduces an n by n matrix to the identity matrix I, what effect does the same sequence of operations have on the matrix I? It's going to turn it into the inverse of A. What is the entry in row I in column J of transpose of A if A equals A lowercase, it's a matrix and it's denoted A sub ij. What is the entry in row I in column J? Transpose of A? Okay, so it's going to be A sub ji. Suppose that A is an invertible n by n matrix and B1, B2, Bn are n by 1 column vectors. What information does the reduced row echelon form of the partition matrix A, partition B1, partition B2, partition Bn provide? It's going to provide the answers to the solution sets for AX equals B1, the solution set to AX equals B2, the solution set to AX equals Bn, and all of them in between. The last n column vectors in succession are the solutions of the systems AX equals B1, AX equals B2, and so on to Bn. What is a diagonal matrix? A diagonal matrix is a matrix in which all of the entries off of the main diagonal are 0. Should I say square? I didn't, but I didn't say square. All right, we'll say bad. We'll say hard, even though technically I'm correct. I don't think any other matrix, if it's not a square, doesn't have a main diagonal. But what can you say about the number of solutions of a linear system AX equals B for which the coefficient matrix is invertible? Essentially, what can you say about the number of solutions? There's exactly one solution, and that is X equals the inverse of A times B. All right, that's it. So I'm going to grade what I did yesterday. Then I will be back to recall how I did or state how I did and continue going from there. So I'll be back in a bit. All right, I got both of those, the proof and the true or false, correct. However, I did get a hint from ChatGPT yesterday for the proof, so I marked it wrong in textbook, but we're good to keep moving forward. So I'm going to go ahead and finish up potentially the last of 1.7 right now. So talk to you in a bit. All right, guys, there you have it. 1.7 problems are done. 2 more true false questions that I finished were, here we go, G. This was asking if a diagonal matrix is invertible if and only if the entries are in the main diagonal are positive. That's false. It's invertible if and only if the entries of the main diagonal are non-zero, so they can be negative as long as they're not 0. This one was asking if A plus B equals an upper triangular matrix, then A plus B are upper triangular matrices. That's false. As a counterexample, here we go. A plus B, neither are upper triangular matrices, but you result in an upper triangular matrix. Then this last one was basically take this formula, which solved for 4 invertible partition matrices, A, B, C, D, except do it for a diagonal. Find the formula, and B equals this, C equals that. 0, that is, because it's diagonal matrix. Ultimately, you can do it all. I didn't do all of it because I just realized this is what it is. Inverse of A, inverse of D, 0, 0. And then using the computer, I solved for a given, or I found the inverse of a given matrix using that formula. So there you have it. 1.7 in the books. Tomorrow we'll begin 1.8. So talk to you then.